No, dialogue. So yeah, dialogue is obviously a very exciting topic that goes into lots of systems that at least I use frequently. Like when I call when you call just about anyone, any company in the US, you use a dialogue system nowadays. Also, if you have an assistant like Siri or Google Assistant or something like that, you're using dialogue quite frequently. So important broad spanning topic. We're very lucky this time to have a TA who is an absolute expert on dialogue and has done work on many different aspects of dialogue systems, Shikib. So without further ado, I'll turn it over to Shikib to do the lecture today.
Okay, hi everybody. My name is Shikib. I'm a PhD student, fourth year PhD student working on dialogue. And yeah, today I'm excited to talk about dialogue and introduce the concept to you guys. Okay, so what is dialogue? Dialogue is essentially natural language processing for conversations. That involves understanding utterances in the context of a conversation, and then also generating responses. You need to generate responses that are consistent and coherent with the dialogue history, and then also responses that are interesting and engaging, and that meaningfully progress the dialogue towards a goal. So throughout this class, you guys have learned a lot about different NLP problems. So what's new in dialogue? First of all, the notion of the dialogue history is the biggest thing that is new in the problem of dialogue. So the dialogue history requires you to consider an utterance in the context of the dialogue history. You must also understand the back and forth interaction and estimate a belief state over user goals, resolve co-references, and so on. And then also the other thing that's new in dialogue, in addition to the dialogue history, is that there's often this communicative goal. So like there's a goal or a purpose to a conversation. In task-oriented dialogue, you often need to progress dialogue towards some goal or to complete a task. And then in open domain dialogue, the goal of your dialogue system is to produce interesting and engaging responses. So basically in dialogue, there's new challenges, there's new tasks, and new models. The new challenges, as I mentioned, include modeling dialogue context, the goal-driven nature of dialogue, task-specific terminology, and the problem of one-to-many responses in open domain dialogue. In terms of new tasks, we're dealing with response generation, NLU, and NLG, as well as dialogue evaluation. And then also dialogue has a lot of new models, some of which I'll be talking about over the course of this lecture. So my objective in this lecture is for you guys to walk away with knowledge of the unique challenges that are present in dialogue, knowledge of the different tasks and data set that are commonly studied in dialogue, and then knowledge of the common models and strategies for dealing with some of these unique challenges that are used in dialogue. So in this lecture, we're going to be talking about response generation, both task-oriented and open domain response generation. We're also going to be discussing NLU and dialogue evaluation. And feel free to stop me at any time with questions. So the problem of response generation is essentially, given some dialogue history like the one shown on the left, we want a model that will read the dialogue history, interpret it, understand it, and produce a meaningful response that progresses the dialogue. What's pictured on this slide is an open domain conversation. There's not necessarily a goal to this conversation. You kind of just have the user and the system chatting with each other. But you can tell that the system's response is good because it meaningfully progresses the dialogue and demonstrates that it understands the dialogue history. Here's another dialogue context and the corresponding system response. In this case, you can tell that the user has a goal for this dialogue. The user is asking the system to provide it a good Italian restaurant in the Oakland area. And the model responds with a relevant response. And often in task-oriented dialogue examples like this, your model isn't just reading the dialogue context, interpreting it, and producing a response. It also needs to interface with like a database or some knowledge source or so on. Okay, so we're going to start by discussing task-oriented dialogue. And the purpose of task-oriented dialogue systems is to interact with the user in order to complete a specific task. On the slide here, I have listed a couple of my favorite data sets for task-oriented dialogue. There's a lot of data sets for dialogue, but multi-wells especially is one that people have been using a lot over the past few years. The other ones are, some of them are more recent, and yeah, I think they're all pretty solid data sets. So the goal of task-oriented dialogue systems, as I mentioned, is to interact with the user in order to complete a task. So what does this require? The dialogue system must first understand the dialogue context. It must track the belief state over the dialogue context. And what I mean by this is when the user is providing specific attributes or like requesting specific things, over the course of the dialogue, you need to update and you need to track the belief state. So like in the first example that I showed, the belief state might be something like user requested restaurant, neighborhood is Oakland. You often need to interact and interpret with a structured database. And then you need to follow a task-specific dialogue policy. And this is something that is really important in task-oriented dialogue because unlike open domain chit-chat systems where you can respond with whatever, in task-oriented dialogue, there's generally a policy that's known beforehand. And then you must also generate natural language responses. So here is a pipeline dialogue system. This is essentially how people did task-oriented dialogue for like years before deep learning was a thing. So here, basically what's happening is we have some dialogue history, the context, and the dialogue history goes through some natural language understanding module. From the natural language understanding module, we get a belief state over the dialogue history, and then the belief state is passed to some dialogue manager. This dialogue manager interacts with the belief state, interacts with external databases, and determines, according to the dialogue policy, what is the appropriate system action. And then once that system action, the dialogue acts are generated, that's passed to a natural language generation module, which honestly in these kind of systems is often just a template-driven thing. And the natural language generation then produces a natural language response conditioned on the dialogue acts and any other information.
So you said these were used before deep learning was a thing. My impression is that still most of systems are.
Yeah, that's true. Except like a lot of the time, some of these modules will be based on deep learning. Like I think like at somewhere like Alexa, the NLU will always be like a BERT-based model. Okay, so talked about this. Okay, so here is this is like one of the simplest models that you can have for task-oriented dialogue. And this is essentially what was introduced along with the multi-wells data set. So if you ignore everything on the left-hand side of this diagram, this is really straightforward. What's happening here is you are encoding some dialogue history and then with like an LSTM encoder. And then you have a decoder that attends over the encoded hidden states. What is slightly different here and why this isn't just seek to seek with attention is that the database, some like database vector, as well as some Oracle belief state, is incorporated into the final hidden state of the encoder with a linear layer. So basically what's happening here is we are encoding the dialogue history. We are combining it using a linear layer with the database vector as well as the Oracle belief state, and using the result of that concatenation to initialize the decoder. So this is like the most straightforward model for task-oriented dialogue. So structured fusion networks were kind of the next thing that was done on the multi-was corpus. And this was work that was done by me. So because this diagram is a bit confusing, we can kind of break this down. So basically, in structured fusion networks, we begin with neural modules for the NLU, the DM, and the NLG. And as I showed in the pipeline dialogue system diagram, the NLU goes from some context, the dialogue context, to a belief state. The dialogue manager goes from the belief state and some database vector to the dialogue act. And the NLG goes from the dialogue act, as well as the belief state and the database vector, to natural language. So if we were just to take neural models and try to mimic the pipeline dialogue system paradigm, we would just pass them along. We would just pass in the outputs from the NLU into the DM and the outputs from the DM into the NLG. Yes? So in the multi-was corpus, and I think this is like a terrible way of dealing with this, but in the multi-was corpus, the database vector is fixed for every input-output example. Yes, yes. But if you don't know it beforehand, the way of dealing with it is basically like to take the belief state, transform it into an SQL query, and then query the database. Yep. Okay, so a dialogue act is essentially like, it could be something like inform restaurant. So what it means is tell the user the name of the restaurant, or like inform price, tell the user the price of whatever they're asking for. It's just, go ahead. Yes, yeah, it's a category that's predefined and indicates what the natural language response from the system should try to accomplish. Yes. Yeah, so in this case, what we did was we had intermediate outputs, we pre-trained them separately, and then we also tried fine-tuning this, like as for the task of response generation. But that doesn't really work that well on its own. So what we ended up doing was we took, like if you see in these black boxes or these gray boxes in the middle, we have that NLU, DM, and NLG modules. But we also learn a seek-to-seek network on top of these modules. And essentially what this does is it combines these structured intermediate outputs of the NLU, the DM, and the NLG with a higher level model on top of this. Does that make sense? Like there's a lot of arrows here, but the concept is really simple. Like you just have a model that at each like stage takes inputs from different pre-trained components. And then work that was done more like since structured fusion networks, a lot of it has kind of built on this concept of sequentially relying on these intermediate outputs, but they've done it in much simpler ways, in my opinion. So Soloist, which was a paper that was released last year, essentially took a GPT-2 model and it trained the GPT-2 model to first generate the belief state. And then, as I mentioned, like once you have the belief state, you can kind of deterministically get the database state. And then given the concatenation of the dialogue history, the belief state, and the database state, you can auto-regressively generate a response. So this kind of takes the idea of structured fusion networks, and rather than having this like complicated architecture with LSTMs, you just use GPT-2 to sequentially generate everything. And then Simple Todd it's kind of the same concept of sequentially generating things, but then they also generate, in addition to the belief state and the database vector, they also generate these system actions, the dialogue acts. But the concept is basically the same thing. And then also Simple Todd generates a SQL query as well, rather than just using the database vectors. But the main takeaway here is that in task-oriented dialogue, it's often beneficial to think about the structure that is provided to you by these intermediate outputs and try to leverage them for like the task of response generation. Any questions there? Yeah.
Maybe you could explain a little bit about the whys and multi-whys, how they actually.
Okay, sure. So the WOZ framework, which is the Wizard of Oz framework, is basically a way of collecting data where you have it's a way of collecting dialogue data specifically. I don't think it's used for any other task. But basically the idea behind the WOZ framework is you have a human that is playing the task of the dialogue system, that is playing the role of the dialogue system, and users are interacting with this person. In some cases, they believe that they're interacting with the dialogue system. In some cases, they know they're talking to a person that is pretending to be a dialogue system. But in the multi-WOZ case, users were given kind of they were given a scenario that would set something like, oh, you're at a hotel right now, you want to get to a restaurant, so like ask for a taxi and then ask for a restaurant reservation, and the user would then ask for that stuff while the person that was playing the role of the system or the wizard answer those questions and progress the dialogue. Does that make sense? Okay, awesome. And then the last model that I'm going to be talking about for task-oriented dialogue is Marco. And Marco's kind of based on the same philosophy as all the systems that I've already discussed, where they use intermediate outputs to kind of structure the process of response generation. Here, what they do is they have a shared encoder, which looks at the dialogue history as well as the database vector. And then they have two decoders. They have a response generation model, response generation decoder, which generates a natural language response. But then they also have this dialogue act decoder. And the dialogue act decoder generates the dialogue acts that are necessary for a system response. And these are kind of like, there's annotations for the dialogue acts. But then what's interesting here is that the response generation decoder is able to attend to the dialogue act decoder's hidden states in order to like better inform the generated responses. Does that make sense? Okay, cool. So that was task-oriented dialogue. Now we're going to discuss open domain response generation. So in contrast to task-oriented dialogue, where there's kind of a goal that you're progressing the dialogue towards, and like there's these structured outputs, intermediate outputs, and like there's kind of a constrained space of potential responses. In open domain dialogue, systems must engage in chit-chat with the user. The topic is often unbounded, and users and the system can talk about anything. I've listed here 5 open domain dialogue datasets, and these datasets are fairly good. The one problem with open domain dialogue is that these days a lot of people aren't just training their systems on one data set and then evaluating it on the same data set. What they're often doing is they're training it on like all of Reddit or something, like very large open domain conversation data sets. And it makes it really hard for people in academia to kind of compete, but these are just the data sets that you would evaluate on, perhaps. So the goal of open domain dialogue systems is to engage in chit chat, which means that they must understand the dialogue context. They must be able to discuss a variety of topics. They must generate natural language responses, and they must generate interesting and engaging responses rather than just dull and generic ones. And also, dialogue systems must have some degree of common sense reasoning. So one of the earliest open domain dialogue systems this was in 2015. Basically, what they did was they flattened the dialogue context and they concatenated to the response and kind of just trained a language model. And you can see on the right-hand side that this dialogue system isn't particularly good. It generates things that kind of seem correct, but like if you look at it closely, it's not coherent, it doesn't make much sense. It kind of shows that just like an LSTM language model can't do that much. This is a hierarchical encoder decoder, and they kind of take a step forward from just like the flat seek to seek. And what they do here is they have a hierarchical setup where there's an utterance level encoder that encodes the words in a single utterance and produces a hidden state. And then there's a context encoder which takes the sequence of hidden states and encodes those. Yep. Yeah. What do these, well, there's no great way of measuring this stuff directly. And that is a problem that I'm going to be talking about later when I talk about evaluation. But yeah, like often human evaluation of the final responses is the only way to reliably measure the quality of open domain dialogue systems. There's no great way of measuring any of these things independently. So another big problem in open domain dialogue systems is or was the fact that they often generate dull responses. And what I mean by this is if you just train like LSTM seek to seek on some data set, what often happens is it'll just start generating very generic responses like, I don't know, or okay, that's cool, like something very generic that is present in a lot of the data set. And that's known as the dull response problem. So this work, in order to mitigate the dull response problem, they propose a diversity promoting objective function. And they use MMI rather than cross entropy as a loss function. And basically the objective there is to avoid like this generic response problem by using maximal mutual information rather than just like optimizing for the words being correct. They also add a term to their loss function that penalizes high likelihood responses, and this is kind of like an anti-language modeling objective. And the results are, I mean, they're not amazing, but if you look at the right-hand column, there's a lot less generic I don't knows or like I don't know X than there is in the middle column. Another thing that people did in order to make open domain chit chat models more consistent as well as more engaging is they conditioned response generation on personas. So what would happen here is that a response generation system would have a set of facts that serve as their persona, things like I like to ski, my wife doesn't like me anymore, I went to Mexico 4 times this year. And those elements of the persona were basically like the people that collected this data set included them throughout the dialogue. So like by virtue of that, the dialogue models learn to include aspects of the persona throughout their conversations. And this is an example of a persona conditioned conversation. Like person 2 here is the dialogue system. And if you look at it, there are attributes of the persona communicated throughout the dialogue, but it's still like fairly, it's not that great. The problem kind of is that when this data set was collected, the persona chat corpus was collected, the annotators often, like their definition of the task being complete was kind of whether all of the elements of the persona were communicated in the dialogue. So what they often did was they just like try to include one fact from their persona in every single utterance. And what happened was like the dialogue doesn't really flow. It's just two people trying to share as much about themselves as possible, which is not really how humans talk. And then this model is Transpo. And this model is actually the first time I heard about Hugging Face. There was a competition in 2018 run by Facebook and some people from Montreal. And basically the point of the competition was for people to build response generation models on the persona chat corpus. And there was this one team that on the automatic metrics leaderboard, they were like way ahead of everybody else. And that team was Hugging Face before like even BERT was a thing. So like they were just, their whole company was working on dialogue systems. And they were way ahead of everybody else on automatic metrics with this model. And this model is relatively simple. It's basically just GPT, like the original GPT, not GPT-2, with the persona built into the sequence, the history, and then the response is what they were tasked with generating. But the very interesting thing in this competition is that even though the Hugging Face model, Transpo, was way ahead of everybody else on the automatic metrics, when the organizers actually did human evaluation, the Hugging Face team did not place first. And that kind of, to me, that was a very interesting takeaway because it shows that optimizing for automatic metrics like perplexity and blue score, and I think the other one was F1, does not necessarily lead to a good dialogue system. So like at the end of the day, to determine whether your dialogue system is good, you need to have a back and forth conversation with it and run human evaluation. And that's really the only real way you have, only reliable and trustworthy way you have of evaluating a dialogue system. And then this is Dialog GPT. And basically what they did was they took GPT-2 and they continued pre-training it on conversations from Reddit. So here in order to train it on conversations from Reddit, Reddit is a discussion board for those that aren't familiar, and people reply to each other and you have threads of comments. So it's not really dialogue, but these guys kind of found that if you do some amount of pre-processing, it's good enough to resemble real dialogue. So they filtered long utterances, they filtered non-English utterances, they filtered URLs, and they filtered toxic comments. And they were left with 147 million dialogues, or 1.8 billion words. And they continued pre-training GPT-2 on these dialogues. And according to their paper, they attained human-level response generation ability. So what this means, or the way they came to this conclusion, was given some dialogue context, they had Dialog GPT produce a response, and then they had a human annotator produce a response. And then given like a large set of dialogue context, and then responses from both Dialog GPT and the human annotator, they then asked a number of humans to look at both utterances and determine which one they liked better. And I think the human annotators that were evaluating the quality of the utterances, were given the option of picking one, the other, or saying that it was a tie. And in most cases, it was a tie. And then it was more likely that Dialog GPT was preferred than humans. So like Dialog GPT won a greater percent of the time than humans did. And yeah, like at the time this came out, it was kind of a surprising result, and some people questioned whether it was true or like whether there were errors in the annotation process or in like the response writing process. Like maybe you asked humans that did not generate interesting responses, so that led to Dialog GPT being preferred more often. But regardless of whether the responses are actually human level, they are very good. They are very good, and they're better than any of the other models that I've shown you so far. And I think that this like more or less just comes from the fact that you pre-train on a large amount of data. But what we actually did when some of these very large pre-trained models came out was we took conversations between a state-of-the-art dialogue system that was pre-trained on a lot of data and humans, and we asked human annotators to look at individual responses as well as the entire dialogue. And they looked at individual responses between humans and systems, and then also humans and humans. And what they actually found, what our analysis concluded, was that if you only look at the responses generated by systems, people will actually prefer responses generated by systems rather than responses generated by humans. But if you look at the entire dialogue and you look at like whether they were coherent, whether they were consistent, whether there was any depth to the interaction, or whether it was just like shallow responses or whatever, humans are preferred a lot more than dialogue systems. And what this goes to show is that pre-training is a viable mechanism of generating really good responses, but it's still not at the point where they can have like better dialogues than humans can. Does that make sense? Okay, cool. And yeah, so Mina was the successor to Dialog GPT. Dialog GPT was released by Microsoft, Mina was released by Google, and then Facebook had Blender after this, which like again was really similar. But Mina, basically what they do is they also train on Reddit, but rather than using the GPT-2 architecture, they use the Evolved Transformer architecture. And they use a bigger model, slightly more data, and train for longer. And they have really good dialogues. And these are actually the dialogues that we use in our analysis to determine whether humans were better than dialogue systems at generating responses. And if you look at these dialogues, they're actually really good. Like I was kind of mind blown when I originally saw these in like late 2019, early 2020. Like on the right-hand side, it seems like Mina, the dialogue system, generated a novel joke about Harvard and Harvard and cows. And I think that was pretty impressive. Okay. Any questions about large dialogue systems or open domain or anything? Yeah. Yeah, that is something that people do, and that is actually one way that I think this paper evaluated their systems. It's called self-play, and you just kind of have them talk to each other. You could use it as a way of training them as well, though I haven't seen too much of that in any of the recent papers. Yeah. Yeah. Actually, I'm not entirely sure whether anybody has done a lot of work in like multi-party dialogue. I would guess that it should be possible. Like if you think about the data that these systems are trained on, which is just Reddit, that is it like on its own a multi-party interaction. So I can't think of any specific paper that does this kind of thing, but I'm sure that either it exists or if it doesn't, it would be really easy to do.
I'd just like to give a comment that at one point I was very interested in this, looking at 100 of the dialogues. I looked at 100 to 200 of the dialogues and actually benefited them. And they are really good in some cases. The one on the right, this is particularly special. This is not
It's a cherry-picked example for sure.
This is not anywhere near the average, but overall they're good, and the ones on the left are, the one on the left is pretty reasonable. However, I'd say at least half of them have some sort of inconsistency.
Yeah.
So it's like some sort of inconsistency that wouldn't have in the dialogue. So all of these are public and available online, right? Like my favorite inconsistency is when they're talking about what you did over the weekend, and it's like, oh, I went surfing, but I went surfing, and then the human says, oh, are you good at surfing? And it's like, yeah, I'm from southern Arizona. There was lots of surfing to be had there. And if you're not in the U.S., you might not realize this, but southern Arizona is completely landlocked, so there's no ocean there to be surfing on. But the fact that you need to have that level of knowledge in order to realize that it's wrong is like the level of difficulty, like detecting these errors for the credit. So I think this is a really interesting thing.
Okay. And then Plato II was the successor to Mina, I guess you could call it that. And I actually think that this model or this paper and this model, they're a lot more interesting than kind of like either Mina or Facebook's Blender is, just because they do something that is actually interesting rather than just scaling up the training and the model and whatever. And the idea here is that you start with just a regular response generation training, and then you move on to simultaneously training for diverse response generation and response coherence estimation. So this is kind of like the motivation here is that there's a one-to-many response problem in dialogue. And what that means is that for a single dialogue context in open domain dialogue, there's many things that you can say that would be valid responses. So when you train a model for just response generation, what might happen is like the model might kind of flip-flop, like it might generate the first thing that you wanted it to, and then you tell it like, no, you should actually be generating this response. And then later on, it generates the second response, but you tell it, no, you should generate the first response. Also, it makes evaluation really difficult, which I'll discuss later. But so they first train just general response generation, and then they train diverse response generation, where there's a latent vector that tells it what should the generated response be. And then they also train a response coherence model where you have the context and you have the response, and the objective is to determine whether the response actually does match the context. Yeah. For the what? Okay.
Yeah, so this is a really good question. Just to repeat the question, it's like, is there a way to enforce that machine-generated text is actually true? So one way that you can do it is template-based language generation and a well-curated knowledge base or something like this. So like basically what you're doing is you're creating something that's so restrictive that there's no way it could generate anything that's false. And this is practically what a lot of dialogue systems do use, but it's also too restrictive to do anything nearly as interesting as what Mina is doing, right? So I think the problem is, do you want to take a model like GPT-3, which can do really amazing things, but can also completely make up facts that are wrong and try to make it more factual? Or do you want to take the highly factual template-based thing that is, not very flexible and try to make it more flexible? I think those are the two directions. And in terms of making like a language generation system more factual, there are methods where you can try to detect factuality. There's like factuality prediction methods for things like summarization, and you could probably do them for dialogue responses. But like for the Southern Arizona example, that'd be really hard. Like you need to have geographical knowledge. I think like verifying it is almost as hard as, creating a system that can generate it itself. So I think it's a really interesting challenge that right now, like there's no good solution for.
There was a funny example of that on the Big Jeopardy challenge, where the host was from Canada, and the system thought that Toronto was in the United States. And if you look at it geographically, it's right between New York and Minnesota, and so that might make sense. But anybody knows anything about North America knows it's Toronto in Canada. And this is a big fancy system that IBM spent millions of dollars.
Yeah, so, and like, you can make things better, but completely preventing it from saying anything that's wrong ever is going to be very hard, I think. So, yeah.
Cool. Yeah, so this is Plato II, and this is a interaction that somebody had with Plato II. And I think this is really impressive. And I talked to the system a decent amount, and it like consistently generates really good dialogues like this. So to give some context, sometime last year, in part motivated by the example in the Mina paper where, or like the thing I talked about with the Mina dialogues, where we saw that the dialogue level quality was a lot worse than looking at individual responses. We ran a challenge at AAAI where basically what happened was we challenged people to take really good response generation models and get them to work really well for back and forth interactions with real users. And the Plato II system was one of the ones that was submitted to our challenge. And I think they won the challenge, but they either won or they came second, but the dialogues were really good. And they built a lot of things on top of the model that I showed on the last slide, where they, like for example, they trained the model in this way, but then they took this like response coherence estimation component and used it as an evaluation model to rank their the set of responses that were generated by their diverse response generation component. And they did like a lot of post-processing and like filtering, and like I think they might have had something in there to reduce non-factual responses as well. But regardless of what they did, I think this interaction was really impressive. It's able to like talk about very specific things in two different areas at the same time here. And
Sorry about the question. Another question is, I think some people in the press might be interested in which of these you can actually use.
yeah,
Because I know a lot of these are not made.
yeah.
But I guess
Plato II is public. It is a bit hard to use because I think you need a larger GPU. Dialog GPT is public. I've used it a lot. It's really easy to use. It's on Hugging Face. For Plato II, I think you need to install whatever framework Baidu has. I think it has a Q in it. I don't know if you know what I'm talking about. But that's kind of annoying to set up, just in case anybody was thinking of doing that. But Dialog GPT is public. Blender, which is Facebook's model, is public. Mina is not public. And I talked a bit about open domain dialogue, but there's a lot of things that I haven't really talked about, like knowledge grounded response generation, persona grounded response generation, negotiation or persuasive dialogue, common sense dialogue, and conversational QA. These are all things that you might potentially want to work on. Knowledge grounded response generation, the topical chat data set, as well as Wizards of Wikipedia, are both really good data sets for this task. So before I move on to NLU, are there any questions about open domain dialogue? Yeah. For knowledge grounded response generation, there is topical chat and Wizards of Wikipedia. They were on my first slide with the list of data sets. And then for persona grounded, there's persona chat. And if you're interested in any of the other three, like send me an email or post on Piazza and I can share data sets for the other ones. Okay, so we talked about response generation. The next thing we're going to briefly discuss is natural language understanding in dialogue. There's several key tasks, intent prediction, which is like asking the question of what is the user's intent or their goal, slot filling, what are the slot values, like did the user provide a time, did they provide a neighborhood, did they provide a date, state tracking, which is tracking the user's information or goals throughout the dialogue. So again, I'm kind of advertising my work here, but we introduced the Dialog Glue benchmark, which takes a number of tasks related to NLU and dialogue and provides a benchmark that you can evaluate them on. For intent prediction, these are a couple of good data sets: ADA, SNPs, Banking 77, Clink 150, and HWU 64. For slot filling, again, ADIS and SNPs. ADIS and SNPs are kind of older data sets from like 10, 15 years ago, whereas the other ones are a bit newer. So, and then, okay, so ADIS SNPs, DSTC8 SGD, and Restaurant 8K are good slot filling data sets. And then for state tracking, really like the main thing that people are using is multivos. Multivos had a lot of problems, but like people keep fixing the problems and releasing new versions of the data set. So like, I don't know whether we're on multivos 2.4 or 2.5 now, but whichever is the newest one is, I'm sure, a really good data set. Okay, so the first paper that I'm going to talk about is for NLU is addressing the problem of slot filling. And I really liked this paper when I read it. The idea here is that they're introducing a pre-training paradigm that is specific for slot filling in dialogue. And what this results in is stronger few-shot and zero-shot performance. So they basically try to take data from Reddit, which I mentioned before, is kind of like a suitable proxy for dialogue, though it's not exactly dialogue. So what they did was they identified these entities, like where Toy Story 3 or 64 gigabytes is an entity, and they identified places where this occurs multiple times. So during their pre-training, they essentially took like a template, they took one of the sentences in which it appears, and they replaced the name of that entity with a blank or like a mask or whatever. And then they took the input sentence as their, like they have the template sentence with the entity blanked and the input sentence with the entity not blanked. And the objective of the model was essentially to identify which set of words in the input sentence match the blank in the template sentence. Does that make sense? So I think this is really interesting because they essentially came up with a creative way to take this open domain dialogue data, quote unquote dialogue data, and use it for this like very task-oriented task of slot filling. And yeah, this ends up working really well. I'll show you some results in like 3 or 4 slides of this model. But it does a lot better than any prior work on this data set. And then as kind of like building on the idea of the convex model, recently I had this paper called GenSF. And when I read the convex paper, my takeaway there was that the reason this works so well is because you are, rather than taking the pre-trained model, like taking any generic pre-trained model like BERT and trying to force it to work well for your task, what the convex paper does is they kind of try to achieve a stronger alignment between what is learned from the pre-training and what is required for the downstream task. And they did this by like proposing a pre-training paradigm that like requires a lot of GPUs and like a longer amount of training. But I thought that perhaps one other way to do this would be to modify or to reformulate the downstream task to be better aligned with the capabilities of a pre-trained model. So I took Dialog GPT, which, as we saw earlier, quote unquote, human level response generation. And I took like task-oriented slot filling and tried to reformulate it into a response completion task. So like, if the dialogue is something like, what is your first name, what is your last name? And then they give like this Loris Heusel, I'm not sure how to pronounce that. Then essentially in this GenSF paper, we reformulate the question of whether first name exists in here as what is the first name, last name, Loris Heusel, okay, the first name is, and then pass that as input to the model. And the objective of the model, of the Dialog GPT model, is to attend to the input and complete this response. And in addition to reformulating this, we added a lot of other augmentations, like we added a copy mechanism, constraint decoding, some post-processing mechanism. But the idea here is like relatively simple, whereas Convex designs a pre-training mechanism that achieves stronger alignment between the pre-training and the downstream task. In GenSF, we just reformulate the downstream task to work well with a specific model. In this table, we compare the results between SpanBERT, which was the previous state of the art, Convex, and GenSF. And if you see, the rows of this table are basically how much of the training set are we using. When we use 100% of the training set, like Convex and GenSF are doing well. They're doing slightly better, but not significantly better. But as we go down to like 1/128th of the training set, where we have 64 training examples in total, SpanBERT is at about 30.6, Convex is about 71.7, and GenSF is at 72.2. And like GenSF, again, achieved these results without doing any like significantly large pre-training like Convex did. And the other interesting thing is that because of the way these models were built, they can be used for zero-shot slot filling, where we do absolutely no training whatsoever. Convex, they reported their zero-shot slot filling results, and that's in the middle column. And there's an average of about 5.2 F1 score. Though actually what they did, like the real problem with their approach is that things that are not actually slots are often identified as slots. Like the precision of this model is very low. In contrast, GenSF gets about 19.5, and we have another model there, Coachless TR, which was specifically designed for zero-shot slot filling, and they're at about a 10.7 F1 score. So I think that's all I have about slot filling. Any questions there? Yeah. So oh yeah, sorry, I think I wasn't particularly clear about this. So Convex pre-trained on this data set, but then they evaluated on the restaurant's 8K data set. And that's also what both, like all these results are evaluated on the restaurant 8K data set. Yeah. I see what you mean. It's evaluated on the reformulated version, but the results are mapped back to the original. So the reformulation can be thought of as like a pre-processing step, or like part of the model, basically. Okay, cool. Okay. So this is the tricky model, and this is a model for state tracking. It's currently the state-of-the-art model for state tracking. And although I think this paper is not the state-of-the-art, all of the models since then have just been building on Trippy. And if you're interested in state tracking, I would highly recommend you check out this paper. But the concept here is that the Trippy architecture essentially tries to generate a dialog state by attending to three things. That's a triple copy mechanism. That's where the name comes from. They are attending to the previous dialog state, the system inform actions, and then also the user utterances. And by having three different copy mechanisms and having three sets of things that you're attending to, the Trippy model is able to achieve really good results on state tracking. And this is an example of how state tracking might work. Like in the first utterance, the user says, I'm looking for an expensive restaurant in the center of town. And expensive and center are attended to and added to this ongoing state that is being tracked. And then also like the system informed, can be what that says, it's Billy's restaurant. And when the user says that sounds good, that fits Billy's restaurant that was informed by the system is added to the dialog state. Any questions about state tracking? Okay, awesome. So the next topic or problem area that I'm going to discuss is dialog evaluation. And the goal with dialog evaluation is to construct an automatic evaluation metric for response generation or interactive dialogue. So in dialog evaluation, we're given a dialog history, a generated response, and optionally a reference response. And the objective is to generate a score that corresponds to the quality of the response. So why is this hard? The first reason that it's hard is the one-to-many nature of dialogue. For each dialogue history, there are many valid responses, and therefore, unlike many tasks like machine translation, in dialogue, it doesn't make sense to compare to a reference. The reference response isn't the only valid response, and because of this, it means that existing metrics like Blue and F1 score don't work well, because you can't just take one valid thing that somebody could have said and say that this is the only valid thing the dialogue system should always say. Dialogue quality is also multifaceted, so it doesn't really make sense to boil things down to a response being good or being bad. For the purposes of interpretability, we should be measuring multiple qualities like relevance, interestingness, and fluency. And then the final reason is that dialogue is inherently interactive. The goal of dialogue systems research is to build models that can have a back and forth interaction with the real user. And right now, research, or like for the most part, research largely focuses on static corpora, which reduces the problem of dialogue to response generation. And as we were kind of discussing earlier, when you look at these state-of-the-art dialogue systems like Mina and Dialog GPT, they produce really good responses because that's what they've been trained and evaluated for. But once you ask them to have an interactive dialogue, they kind of fail. And there's some properties that can't be assessed outside of an interactive evaluation, like long-term planning, error recovery, and coherence. Consistency kind of fits in here, but there are ways of evaluating consistency with response generation as well. Yeah, so to sum up, evaluation is difficult because we can't compare to a reference. We want to assess many different aspects of dialogue quality, and we should be evaluating in an interactive manner. Any questions about that? Yeah. Yeah. Okay. So yeah, that's a really good question. So these problems that I'm mentioning are more so for open domain dialogue and for chit chat. And the reason that these problems are more significant there is because the space of possible responses is a lot bigger, the space of possible valid responses. For task-oriented dialogue, there's often a constrained space of what can or what should be said, so it's easier to evaluate. And oftentimes, though it's not necessarily perfect, Blue Score does a good job at just evaluating the quality of the responses. And then there's also metrics like you mentioned, designed to measure the task success. The multi-WAS data set, for example, has inform rate and success rate in addition to Blue Score as its evaluation. And those metrics are essentially measuring whether the right information was provided to the user rather than necessarily whether the language was exactly the same as the reference response. There's also, like, for interactive evaluation, you could, like, if you're having a back and forth interaction with the person, you could also determine whether the task actually succeeded, like whether the final goal of the user was achieved.
I'd like your comments on this too, Shikib, but I think one thing that makes task-oriented dialogue harder than open domain dialogue is uncertainty in the belief state. Also, so like you can't always necessarily know exactly what the person was asking for when they made an utterance, and because of this, you know, this won't show up a whole lot in your Wizard of Oz data set because the speakers are humans, and the humans can always kind of like parse the utterance appropriately and understand what the person was asking for. So I don't know what like modern systems are doing for this, but it used to be in older systems that they were very careful about like saying, oh, maybe I have 70% certainty that this person is asking to buy a ticket to Pittsburgh, but they might also be asking to buy a ticket from Pittsburgh. And when I'm not absolutely certain about that, I should be like asking them again and stuff like that. So that's something that's probably more difficult. You can gloss over it in an open domain conversation where you don't really need to cover individual information, but you can't do it in a task-oriented conversation.
Yeah.
So there are also things that make task-oriented harder.
Yeah, for sure. Yeah, I think like with multi-WAS, a lot of people, or at least before this year, a lot of people were using the Oracle belief state just because of the difficulty and the importance of tracking the belief state over the dialogue. But recently there was, I think there was a challenge, and then there was also a big paper where they were tackling the problem of end-to-end evaluation or end-to-end response generation for task-oriented dialogue. I think it was best paper at SIGDIAL last year. And they did some evaluation as to whether the quality of the final response was impacted by the quality of the accuracy of the belief state and whether the errors would propagate because of that. So if you're interested in dialogue evaluation, and I highly recommend this, by the way, because I think this is like, it's a very doable project that for this class, and like it could, I think this is still like a relatively new research area. And there's a lot of potentially interesting things that could be done here. But what I've listed here are a couple of data sets for dialogue evaluation, user grade, holistic eval, DSDC6, FED, and DSDC9. And if you're interested in doing dialogue evaluation as a project, a few months ago now, I think, we came out with this paper a comprehensive assessment of evaluation metrics. And the repository makes it really easy to take a proposed evaluation metric and evaluate it on like 6 or 7 different data sets and a number of different evaluation settings. So if you're interested in doing dialogue evaluation as a project, check out our repo. So one of the earliest, or like one of, not necessarily the earliest, because people had been doing dialogue evaluation in like 2017, but I guess this is like the earliest of the new wave of dialogue evaluation metrics. So maybe briefly, I'll just mention that in early like 2017, 2018, there were some people that realized that dialogue evaluation metrics like Blue and stuff were really bad, and they proposed a model called Adam that was essentially trained on a data set of dialogue histories and corresponding responses, and was able to predict the corresponding quality score by training on annotated examples. But of course, there's a lot of problems with that. For one, they were still relying on a reference response. And as I mentioned earlier, it doesn't really make much sense to rely on a reference response in the context of dialogue. But the second problem is that they were relying on an annotated data set. And this is a problem for several reasons. Like, first of all, if you have an annotated data set for dialogue evaluation, your evaluation metric is only reliably going to work well on the data set that you trained it on, or like the domain of the data set that you trained it on. And then, yeah, I guess those are the two main problems. They still relied on a reference response, and then they trained on a specific data set. Since 2020, like from ACL of 2020 up until now, there's kind of been a lot of work being done on dialogue evaluation. Almost every single one of the metrics since ACL of 2020 until now that has been proposed, and there's been like 10 or something, most of them do not rely on a reference response, and most of them do not rely on any training data. They're all more or less self-supervised, and they're all reference-free. So user was one of the first ones at ACL of 2020 that tackled this problem of dialogue evaluation. And in user, what we did was we took 5 different qualities of dialogue: understandable, natural, maintains context, interesting, and uses knowledge. So we annotated a data set of responses for these 5 qualities, and then we trained models in a self-supervised manner to essentially act as proxies for these 5 different qualities. So mass language modeling, for example, aims to model whether a response is natural. Dialogue retrieval models whether a response maintains context and whether it's interesting. And fact-to-response selection models whether a response uses knowledge. So given these 3 different self-supervised models that model these 5 different qualities, they're then combined through some kind of weighted sum to produce an overall quality. Any questions about that? Okay, cool. So GRADE was another one of those early models for dialogue evaluation. What GRADE does is GRADE does not model multiple different qualities of dialogue, but the interesting thing that GRADE does is they use ConceptNet as a mechanism for generating a graph that kind of maps the topics or like the keywords that are used throughout the dialogue. So like, given the dialogue context and the response, like cats and pet and whatever, those all are combined into some kind of graph. And then that graph goes through like some network. I think it was the graph attention network. And then at the end, you get a vector representation from BERT and a vector representation from the graph, concatenate them, pass them through some feed-forward layers, and then you get an overall quality score. Any questions there? Okay, and then DynaEval is one of the more recent papers on dialogue evaluation. And what DynaEval does is it it takes a dialogue and then it perturbs it in some way to like maybe swapping two utterances or like cutting one dialogue in half and then another dialogue in half and concatenating them together, or replacing an utterance. And then it encodes both of the dialogues through some kind of graph. What they do is they consider the edges. They consider each utterance as a node, and then they compute the similarity between the different utterances, and then run that through a graph convolutional network. And at the end, they have some representation from the perturbed dialogue and some representation from the original one, and they try to predict which one is the real one and which one is the perturbed one. And I think this, according to our assessment, this was one of the better metrics. Okay, so that's all I have right now. Happy to take any questions.
Yeah, thanks a lot.
Okay.
Are there any questions that we have either on Zoom or on like in the room? We had a lot of questions during the talk, so you can stay up here in case there are any. Okay, I guess not, but I haven't thought about dialogue for a while, and this was very informative. So thank you, Shikib. And yeah, I guess that's all for today. And you can follow up with any questions up front.